Okay, we are going to look at how to find limits at infinity. And we've only got two real situations to deal with because we've covered the others. So just to give you a heads up of the two that we know how to do, or hopefully we know how to do, is things like polynomials over other polynomials. And things like things with square roots. Right, those two we've covered. Essentially, don't you just divide the top and bottom? In this top one, don't you divide the top and bottom by the biggest power of x, in this case, x squared? What do you do if there's an x cubed on the top and an x squared on the bottom? What do you do if that happens? Because it cannot.
What was that again?
What do you do if the polynomial on the top is x cubed, but the one on the bottom is only x squared? What do you divide by?
X cubed?
Yes, always the higher power, and both the top and the bottom, right? So you don't say, oh, I'll do the top with a square and the bottom with a cube. That's not going to be a good idea. It must be the same power of x both times. That balances it out. Right, here's the square root one. What would I divide the top and bottom by in this question to find the limit?
X squared.
Agreed. How would I write the top x squared so that it would play well with the square root?
Or square root x to the fourth.
Right. Are we all comfortable with those questions? That's kind of what we did yesterday, right? So, two new guys in time, essentially. Here's the first one. There are no powers of x anywhere in this question, yet we're still being expected to find its limit as x tends to infinity. So what you're going to do here is the same technique, but we're going to adapt it. And what we're going to do is we're going to divide the top and bottom by e to the 2x. And let's see what we get when we do that. Well, if you divide this with e to the 2x, you just get 3. And if you divide this by e to the 2x, you get that. This you get 2. And this you get that. And then you can do brute force. Plug in infinities. So 3 plus 1 over e, well, 2 infinities is just infinity. Okay, let's see what that looks like. Isn't e to the infinity also infinity? Isn't it infinitely large? And isn't 1 over infinity 0? And on the bottom, that guy, which gives me this. So we have now got our answer. So this particular guy, whoops, this guy here, as x tends to infinity, is 3/2. Are we cool with that? Do you need to see another one, or does that seem pretty much the same as the other technique? You just tweak it a little bit, right? To take care of the fact it's not an x squared. In this case, an e to the 2x. Maybe the next time it's an e to the 5x, right? It'll be something like that. Okay, that's the first one, by the way. The second one, there's, by the way, there are only 2 examples of that. They're 23 and 24. The next guy I'm going to do, there are only 2 examples of this, 21 and 22. And we're going to look at how to find the limit as x tends to infinity of, in this case, e to the negative 2x sine x, and this is called the squeeze theorem. It's also called the sandwich theorem if you want to go looking online for examples of it. So this is a totally new technique, right? This is nothing like you've seen before. So what I'm going to do here in my first step is just to rewrite it like that. No biggie, but you get a negative power is the same as a fraction, right? E to the 2x, negative 2x is the same as this guy. Now I'm going to do something rather weird. Why can I say that that limit is guaranteed to be less than this limit? Why is that less than or equal to that? Why can I say that and be sure that it's true?
Because the sign is never greater than 1.
Agreed. You think the biggest number sign is going to be as 1, so isn't that always going to be at least bigger or the same as? Now, what's the other extreme value that the sign could be?
-1.
And so, would you agree that on the other side, that's true? Right? That this limit is going to be bigger than or equal to -1 over e to 2x, right? Because that's the smallest it's ever going to be. This is the biggest. Can you see it being squeezed? Now let's see what happens to this fella. Can you just brute force? Right, e to the infinity is infinity, 1 over infinity is 0. What about this side? Well, how about -1 over e to the 2x becomes -1 over e to the infinity, which is -1 over infinity, and -1 over infinity is also 0. So what do I know about my guy who's squeezed in the middle? Well, the guy I'm trying to find the answer to is somewhere between 0 and 0. Would you agree there's not an awful lot of room there? And so the answer is that that limit is 0. Kind of sneaky, kind of cool. Squeeze theorem. Very specialized question. You typically only use the squeeze theorem when there's a sine or a cosine or a sine squared or a cos squared, right? You don't use it in any other meaningful way, typically. I mean, there are exceptions, definitely. Show you a second one. This one is like 22. That one there was like 21. This one is like 22. So we're going to look at the limit as x tends to infinity, cos squared x over x squared plus 4. Okay, and if I thought about it, I would have, again, I should have wrote it a bit lower. Too late now. Okay. What is the biggest number that cosine squared x could ever be?
Still 1.
Still 1. Now, when you think about cosine, it goes between 1 and -1, right? But when you square cos squared, don't all the negative numbers turn into positives, right? So all the -1/2 become +1/4. So what is the smallest value that cos squared will ever be? And it's not 1 and it's not -1.
0.
Does that make sense? 0's squared is the smallest value that cos squared can ever be. Imagine all the numbers from -1 to 1, right? If you square them, don't you end up with an answers that are always between 0 and 1? Does that help? That's what I'm saying. Now, brute force this side. Isn't that just going to be 1 over infinity squared plus 4, which is 1 over infinity, 0? What about 0 over something? Who cares? The answer is 0. Right? 0 over anything, even infinity is just overkill, right? 0 over infinity is very zero-ish, which means that the guy we're looking for has been squeezed between 0 and 0. And that makes this guy also 0. Called the squeeze theorem. Very specialized thing, right? You don't get to do it a lot. 2 questions is probably the most you're ever going to see. But it's one of those things that if a question pops up, you got to know the technique, because it's not the same as the other things. Are we good with those? Can I move on? The last kind of question we're going to look at is ones that look like this. There are no fractions. There is no technique to these. In fact, you're basically going to find the answer to this by looking at the expression and deciding which piece is the most important part of the expression as far as the answer is when x goes infinite. Would you agree that infinity cubed is going to beat 2 infinities? Would you agree infinity cubed is much bigger than 2 infinities? And don't get in your head infinity is the same guy, right? Infinity squared is bigger than infinity, right? A billion squared has got a lot more zeros in it than a billion, right? It's phenomenally bigger. The reason then that I can do that is that this fella essentially is just that guy, right? That's the only guy that matters. So I only need to find out what that is equal to, and the answer is infinity. You are not going to get a lot of variation in these answers. Do you know the answer is going to be plus or minus infinity? You just have to figure out which one of the two it is. Now I'm going to do the same question, but this time I'm making the limit as x goes to negative infinity. X cubed is still the bigger of the two, right? The highest power of x is going to overwhelm the other terms. What does negative infinity cubed get you?
Negative infinity.
So there are pretty much only going to be 2 answers here, right? Plus or minus infinity, right? What do you think? What do you think that guy's going to get you? Who's going to win?
Two x squared.
Right. Suppose I stick 100 there. Does it help? Still 2x squared. You see,
No,
multiples don't.
it hinders.
Say again,
It
Connor?
doesn't help, it hinders.
Yeah, well, it makes you maybe whatever. I agree. So it's what, 2 infinity squared? So the answer is infinity. How about this one? Which one of those guys do you think is going to be the biggest at the end of the day? Right? When you talk X is a trillion, 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 one of them is going to overwhelm everyone else.
Exponential.
Yeah. Now, a million cubed is big. E to the power of a million is phenomenally bigger. You just trust me on that, it is. So in this case, it's negative e to the power infinity. In this case, then the answer would be negative infinity. So in those questions, those homework questions, there is no real major working. I guess there's a tiny bit of working here, right? But there's not any real algebra. Would you agree? It's just, I recognize hierarchy. I recognize that this is going to be much bigger than anybody else. And that's the only one that I need to focus on, because he's going to, or whatever you want to call it, she's going to overwhelm the whole setting, you know, kit and caboodle. No idea where that phrase comes from, but it's a good one. Kit and caboodle. Right? Are we good to move on? Are you happy about how to do these last kinds of limits at infinity? Pick the one you think is the most important, the one that's going to take over, evaluate it at infinity, and your answer is probably plus infinity or negative infinity, depending on the question. So we are now about to start a new section, and we are going to solve the tangent line problem. You remember way back in week 1, we said, look, differentiation came about from a problem called the tangent line problem, right? What's the slope of the tangent line to a curve at any given point, right? And we started off by getting guesstimates, right? You know, the best we could, but they were always guesstimates, right? We couldn't be sure that we'd got the exact answer. Now we're going to show you that we do have a technique to do that. So here is the theory behind how that's going to work. So I'm going to make this nice and general so it works for any function in the universe, at least theoretically. So I'm going to have a function, what color am I going? Green, I think. And we have a function called y equals f of x. And this function at x equals a, I have a point P, and his coordinates are going to be a comma f of a. Would you agree? If the x coordinate is a, its y coordinate is f of a. And I'm going to have another guy over here, a plus h. And this guy I'm going to call q, and his coordinates are a plus h, f of a plus h. And I am interested in finding the slope of the tangent line. And the slope of the tangent line, the one I'm really interested in, is this blue line here. So this is a tangent. And I want to know its slope. So let's see how we're going to approach this question. The slope of the tangent line, the slope of the line joining PQ. And that's going to be the rise divided by the run. P has coordinates a, f of a, and the other point Q has coordinates a plus h, f of a plus h. Now I want you to think of h, right? This extra little plus h. I want you to think of h as a tiny, tiny number, you know, like 0.0001, right? The tinier, or even tinier than that, right? Really tiny number. So the slope of the line joining P and Q, called a secant line, is its rise over its run, which is the difference in the y coordinates, subtract the difference in the x coordinates. The y coordinate of this guy is f of a plus h. The y coordinate of this guy is f of a. The x coordinate is a plus h. Take away the x coordinate is a. And we can simplify it, not by much, but by a little. And we get this guy. And this is the slope of the line joining P to Q. So far, so good? Now, what will happen if I find the limit as h tends to 0 of the slope of the line joining P to Q? Won't that become the tangent line? If this guy H starts getting closer and closer and closer to P, right? And how does that happen? You make H smaller and smaller and smaller, so you make H go to 0. Now notice it's a limit as H goes to 0. I'm not saying it's exactly 0, it's its limit. Then won't that be the slope of the tangent line? So that's how we're going to solve the problem. The slope of the tangent line is going to be the limit as h tends to 0 of this guy. Okay, let's put that, let's use it. Okay, suppose I have a function, a nice polynomial. Suppose I have x squared plus 2x. Okay. If you wanted to see a sketch of that, it would look something like this. And I would like to know the exact value, right, of the slope of the tangent line at x equals 3. So you imagine that was 3. I'm looking for the slope of the tangent line, right? I want to know, is it a slope of 5 or 45? Now, can you imagine that this isn't going to last long in math? The exact slope of a tangent line at x equals 3 is far too much English. We have notation for that. It's called f dash of 3. So you write it down as f dash of 3. And that means the slope of the tangent line to the curve f at x equals 3. Do you see that's much easier to just write that than it is to write a big long line of English every time? So f dash of 3 is the slope of the tangent line at 3. And Americans call it f prime of 3, but you're wrong, it's f dash of 3. And I'm taking over the world one day, so everybody's going to use dash. Plus it's fun, because you will move on to other professors and you will hopefully say f dash of 3, and the professor will then say, oh, you got Professor Robertson, didn't you? And you'll say, sure did. And you'll then mention that there's a letter of the alphabet called Z that we should all be using a lot of as well, right? So I'm trying to win my victories one little step at a time. So f dashed is that guy. Okay, back to the question. What is that fella? Well, if I call this f dash of a, it's going to be the limit as h tends to 0 of, instead of a plus h, 3 plus h. Take away, instead of f of a, 3 over h. Do you see that the a has become a 3 now? Now, way back in 141, because I know I do this, I told you that one day you are going to be using in calculus this kind of guy, and that you needed to know how to simplify it. Can you remember doing things like that way back in 141? At least if you got me, I can tell you you did. So guess what? We have now reached a point where we need to do this. So let's see what it becomes. The function's called x squared plus 2x, but if you find the value of the function at 3 plus h, what you've got is 3 plus h squared plus 2 lots of 3 plus h. Are you comfortable with that? Take away. F of 3 is what? 3 squared plus another 6, so that's 15. So you take away 15 over h. So the limit as h tends to 0 of, well, if you do that guy, you'll get 9, you get a 6h and an h squared. If you do this guy, you get a 6 plus a 2h, and then you have a takeaway 15. Looks like that. Now, if you combine like terms, some really cool things happen. And it's not a coincidence in this one question. This always happens. Do you notice that 9 and that 6 are 15, and don't they cancel out that guy? So the two pluses, the 9 and the 6, cancel out the negative 15. That's kind of cool. And a little bit of combining while we're at it. An h squared plus an 8h. Now use some of the techniques that we've been dealing with over the last couple of weeks. What should I do next to try and get this limit?
Factor out an h.
Can't I now cancel? And we are left with the limit as h tends to 0 of that guy. Wait a minute, that's just 0 plus 8. That is 8. I can now tell you the exact value for the slope of the tangent line on this curve at x equals 3. That answer is, the exact value is 8. It's not my best guesstimate, is 8. You know, I didn't do a table of values and you know, it looks like it's 7.999 and it's probably going to be 8. This is exact value. So do you see how we bypassed the, well, can't you just make P equals Q? Because when you tried that, didn't you get the horrible 0 over 0 and you were stuck? That we've replaced that by the idea of, you don't make the two of them exactly the same, but if you do a limit as h tends to 0, for all practical purposes, aren't they essentially the same? It's a way of shrinking the question down so that you can get the slope of the tangent line. Kind of clever. That we now have a means of finding slopes of tangent lines by using this guy. Okay. Try the next one. Let's find the slope of the tangent line at x equals 10. Then f dashed of 10, right? Let's use that notation, right? The slope of the tangent line at 10 is going to be the limit as h tends to 0 of 10 plus h, take f of 10 all over h. And that's going to be the limit as h tends to 0 of 10 plus h cubed, we have 2 in front of it. Take away 2000. That's what that is when you plug into it. You're going to trust me on this next one. If you take that guy and cube it, you get 1000, so that's 2000. You then get that guy times that guy, you'll get 100, 300, up to 600. If you do that again and again, you get 10, you get 30, you get another 60, and h cubed. Can you just pretend that I did that right and go and check it yourself in case I screw up? So it's going to be the limit as h tends to 0. And, oops, there's 1,000 there. Those guys cancel out. And I am left with an h cubed, a 68 squared, and a 600h. Just like in the other question, the numbers cancelled out. And just like the other questions, and this is always going to happen, you can pull out an h. And now you can cancel. And so the slope of the tangent line at x equals 10 is basically whatever that guy is when h becomes 0. And I can do that in my head. Would you agree it's 600? You know 2x cubed gets steep really quickly. So a slope of 600 is massively steep, but it's also true, right? That's what the slope would be. Now, if I wanted to find the slope of this curve again, but say at x equals 2, wouldn't the only difference be 2 plus h and 2 here, and much nicer numbers? But I'd have to do the question again, wouldn't I? Essentially from scratch. And if I wanted to know it at -2 or 47.1, couldn't we also do it and it would still work? I wouldn't want to do it for that last one, but it could be done. And we are going to be looking at 3 main situations using this technique. We've kind of touched on the polynomials, so I'll kind of call them done for the time being. We're going to look at square root functions and fraction functions. This technique has got a couple of good things and one really bad thing. The couple of good things is it's very versatile. You can pretty much theoretically at least do it from any function you like. That's pretty good. And I think its second thing is that it does give you the answer, right? It gives you the exact value of the slope of the tangent line. And what's its major bad point? You have to do it separately every time you change the x, don't you? And so that tends to be a very slow process. But think of it as an intermediary stage. We're going to do polynomials like this guy and the one we did before. We're going to do some square roots. We're going to do some fractions. And once we are kind of into the swing of things, we're then going to say, we have noticed a pattern in the answer that we got. And that will allow us to do a shortcut so that when we're finished, I'll be able to do that exact same question in about 30 seconds or less. But we won't be showing you the shortcut until after we've kind of done enough practice at this so that you can be convinced that the shortcut works. Right? In other words, we could do it the long way if we really had to, but the shortcut works and it saves us some time. If we didn't have this chunk in the middle, mathematicians would never accept a shortcut because you have to be able to prove things are true in math. You can't just say, well, it works. I mean, an engineer might say, well, the bridge never fell down, so it's okay to do it that way, right? We don't do that. We prove things. And so we have a foundation that says, look, the shortcut works, but if you want to do it by hand and the long way, you can check it, but it works. That's better than me just saying, hey guys, here's a shortcut for taking a function like 2x cubed and finding the slope of the tangent line. And it's magic. It just works. Trust me, it works. Don't worry about it. You know, get on with your life. That's not very satisfying, right? It just isn't. So I'm trying to sell you on the fact that it's worthwhile to do this. And that's why we spend so much time doing it. Let's try the next fella. In fact, this is going to be the last fella for today. Let's find the slope of the tangent line of this guy at, let's pick an ugly value at x equals 3. So the derivative at 3, that's another name for that guy, f dashed of 3, the derivative at 3 is the limit as h tends to 0 of the value of the function 3 plus h, take the value of the function at 3, and divide it by h. And that's going to become not the ugliest looking function in the world. It'll be that guy. Now, this is going to involve different algebra from the first question. Do you agree? Can you remember doing limits like this? And we had a technique for doing them. And it had a funny name.
Conjugate.
Yeah. And basically the square root plus each other, right? Can you see why we did the conjugate technique? Why we gave you questions in solving limits that needed this strategy? Do you see how it's useful when it's square roots? Now, what happens when you do the conjugate method is that if you want to, this is how I would do it, just write down the bottom two terms again. Don't do anything to them, just write them down. But what's the shortcut for getting the top answer? You could FOIL it out, which will work, but what's the quicker way of getting the answer to the top?
It's like what's inside the square roots, the first thing minus the second thing.
Right. So, yes, you're right. That guy squared, take away that guy squared, is essentially saying the same thing. Now, did you notice that the number disappeared like it did the last time? Do you notice that we got a cancel without even having to do work? That's not always going to happen, but it's nice when it happens. It will eventually pull out an H and cancel if it doesn't, right? So it will cancel eventually. And in this case, it just kind of came out without any real effort. Can we just brute force it now? Can't we just plug 0 in? So what do we get? Square root of 3 plus nothing. Add the square root of 3. Now that's the square root of 3 plus another square root of 3, which is 1 over 2 square root of 3's. Let's rationalize it. And what you get is square root of 3 over 6. Now, the exact value for the slope of the square root of x, which looks like that, at x equals 3, which would be about here. That tangent line, pretend that's a tangent line, I'm really killing it, has a slope, an exact value of that fella. You could not get that answer numerically. If you try to do table of values, you know, like I'll try 3 and 3.00001, don't you just get an ugly decimal? And you might say, well, if I round it off to 6 decimal place, it's nothing 0.123477779 or something, right? That kind of thing. But I defy you to realize that that horrible decimal is the square root of 3 over 6. Would you agree you would never be able to figure that out? Because couldn't it be the square root of 7 over 42? Or a half the square root of 19 over 7, right? It could be anything, right? Do you see that we now have a method that gives us exactly what we want? That is the perfect answer for the square root of a tangent line. It's not an estimate. It is the real answer. That's pretty powerful. And that's where calculus began. From a simple problem of how do you find the slope of a tangent line? And it took us a very convoluted route, didn't it? Then we have to spend forever in the day doing numerical and graphical techniques, and then a whole chunk of how do you find limits and what do they do and why can you do them? And it comes full circle. And now we're back to the beginning, but now we've got a strategy for solving the tangent line problem. And then after solving it, we then tell you, hey, Here's a shortcut for getting the answer. You didn't need to do that in the first place. Well, maybe you didn't need to do it, but now we found a better way of getting the answer. Let's use that instead. Okay, say hi. Oh, before you go and do the bye-bye part of that, I am working on your grading. As soon as this is over and I've answered any of your questions, I'll go back to it. My goal is to get it done by this evening. So, you know, it might be 10 o'clock, but whatever, I'll keep grading till I keel over and fall asleep, right? But